Have you ever gazed at the night sky and pondered, where is everybody? Well, you're not alone. A physicist named Enrico Fermi asked the same question, and thus, we have the Fermi paradox. The Fermi paradox is a conundrum that has baffled scientists for decades. It's named after the brilliant physicist Enrico Fermi, who during a casual lunchtime discussion blurted out this perplexing question. With an estimated 200 billion galaxies in our universe, each teeming with millions, if not billions, of stars and planets, the odds would seem to favor the existence of extraterrestrial life. So, why haven't we found any evidence of it? This fundamental question has led to numerous theories and hypotheses, but none have provided a definitive answer. The paradox is essentially an apparent contradiction between high estimates of the probability of extraterrestrial life and the lack of contact or evidence for such civilizations. One of the primary tools used in this cosmic conundrum is the Drake equation. Named after Frank Drake, this mathematical formula attempts to estimate the number of technologically advanced civilizations that could potentially exist in our galaxy. The equation takes into account factors like the rate of star formation, the fraction of those stars with planetary systems, and the number of planets that could potentially support life. Yet, despite the seemingly high probabilities suggested by the Drake equation, we still find ourselves seemingly alone in the universe. This brings us to the concept of the Great Filter. This theory suggests that at some point from pre-life to Type 3 civilization, a civilization that can harness the energy of an entire galaxy, there is a wall or filter that prevents or makes it extremely hard for life to evolve to the point of significant space colonization. Now, we may have stumbled upon a solution to this paradox, a revelation that might change our understanding of the universe forever. To comprehend the enormity of the Fermi paradox, we need to delve into the astronomical numbers. So let's don our number-crunching hats, shall we? Imagine a vast cosmic arena filled with around 2 trillion galaxies. Yes, you heard that right, 2 trillion. Each galaxy, a whirl of stars spinning in the cosmic dance, is home to an estimated average of 100 billion stars. Now take a pause, let that sink in. But wait, it gets even more mind-bending. If we consider the universe as a whole, we are talking about an astronomical number of around 70 sextillion stars. That's a 7 followed by 22 zeros. It's a number so large that it's beyond human comprehension. And yet, here's where it gets truly fascinating. Among this sea of stars, there's a significant number that are similar to our sun. And these sun-like stars often have planets orbiting around them. Within our Milky Way galaxy alone, scientists estimate that there could be around 40 billion Earth-sized planets orbiting in the habitable zones of sun-like stars and red dwarf stars. 40 billion potential cradles of life just in our galaxy. But the numbers don't stop there. Remember, we're in a universe with 2 trillion galaxies. If we multiply the number of potential life-bearing planets in our galaxy by the number of galaxies in the universe, the numbers become positively staggering. And yet, despite these astronomical numbers, when we tune our telescopes to the cosmos, all we hear is a profound silence. Not a whisper, not a signal, nothing. It's as if we're alone in a cosmic ocean, shouting into the void with no response. So we're left with this paradox. With so many potential homes for life, why have we not detected any signs of extraterrestrial civilizations? With these mind-boggling numbers, the silence seems even more deafening, doesn't it? Two concepts often associated with the Fermi paradox are the Great Filter and the Drake equation. Let's dive into the Drake equation first. Named after astrophysicist Frank Drake, this equation is a probabilistic argument used to estimate the number of active, communicative, extraterrestrial civilizations in the Milky Way galaxy. It's like a cosmic roll call, accounting for factors such as the rate of star formation, the fraction of stars with planetary systems, the number of planets that could potentially support life, and the length of time such civilizations might be able to communicate. Imagine this, a vast cosmic landscape filled with countless stars, each potentially hosting planets teeming with life. It's a thrilling concept, but it's also where the Great Filter comes into play. The Great Filter is a hypothetical concept that suggests there's a barrier or series of barriers that prevent life from significantly colonizing the universe. It's like a cosmic hurdle race, but the hurdles are colossal challenges like the jump from single-celled to multicellular life, or the development of technology sophisticated enough for interstellar communication and travel. If the Great Filter is real, it could explain the eerie silence we've encountered in our search for extraterrestrial life. It implies that somewhere along the path from inanimate matter to a galaxy-colonizing civilization, there's a roadblock that's incredibly hard to cross. It's a sobering thought, considering the potential implications for our own future. So, where does this leave us? Well, there are two possibilities. Either we've already passed the Great Filter, meaning we are among the lucky few to have overcome the obstacles and challenges standing in the way of advanced civilization. Or, the Great Filter lies in our future, a daunting challenge yet to be faced, which could explain why we see no evidence of advanced civilizations out there. Could we have already passed the Great Filter, or is it yet to come? This is the chilling implication of the Fermi paradox. And as we continue to explore the cosmos, we are not just seeking answers about extraterrestrial life, but also deciphering the future of our own existence. Now, let's unveil the much-anticipated solution to the Fermi paradox. The answer we're about to explore is the rare Earth hypothesis. This hypothesis proposes that the emergence of complex multicellular life on Earth required an improbable combination of astrophysical and geological events and circumstances. According to the rare Earth hypothesis, the sequence of events leading to life as we know it is so complex and dependent on such a large number of highly specific conditions that it's incredibly rare in the universe. Let's delve into some of the factors that contribute to this theory. Firstly, the location of our planet in the Milky Way is crucial. We're situated in the galactic habitable zone, an area with the right conditions for life. It's not too close to the galactic center, where radiation levels are high, and not too far, where there might not be enough heavy elements necessary for life. Secondly, the Earth's relationship with its moon is also important. The moon stabilizes the tilt of Earth's rotational axis, ensuring a stable and relatively mild climate. Without the moon, extreme climatic variations would make life as we know it impossible. Then, there are the geological factors. Plate tectonics and the Earth's magnetic field play significant roles in maintaining the conditions necessary for life. Plate tectonics recycle carbon to regulate the planet's temperature over geological timescales, while the magnetic field shields the surface from harmful solar radiation. The rare Earth hypothesis suggests that these conditions and more are not just necessary for life, but are highly specific and unlikely to occur elsewhere. The data supporting this hypothesis is based on our current understanding of life and the universe, which is, admittedly, limited. While this solution may not be definitive, it provides a new perspective on our place in the universe and the mystery of extraterrestrial life. The possibility that we might be alone in the universe is both awe-inspiring and a little daunting. The Fermi paradox compels us to keep exploring, keep questioning, and keep reaching for the stars. As we unravel the mysteries of the universe, we must confront the profound questions posed by the Fermi paradox. With this paradox, we've dared to ask, where is everybody? And in this journey, we've delved into the overwhelming numbers, the statistical probabilities, and the vastness of our cosmos. We've crunched the numbers, examined the Drake equation, and considered the implications of the Great Filter. We've proposed a solution, a theory that could potentially answer this cosmic conundrum. But remember, it's just one of many possible answers. The universe is a complex and mysterious place filled with countless variables and uncertainties. We're standing at the edge of a vast cosmic sea, peering into the depths of the unknown, searching for signs of life in the farthest reaches of space. The solution to the Fermi paradox may be closer than we think, or it may remain one of the universe's greatest mysteries. But one thing is certain, our quest for understanding and our thirst for knowledge will continue to drive us forward into the great unknown.